Thank you all for coming to my talk. I will talk about essentially the idea is how we will evaluate or measure a system's smart level. Right. So let's see. I begin with the motivation. So the motivation is that nowadays there are many smart systems. So we hear about them all the time. So I'll give a few examples. First one is Google. This is the instant search offered by Google. So while you are typing your keywords, Google is actually trying to guess what you want, and they're doing the computation at the back. And so if it guesses right, then after you're done with the keyword, it can give you the result right away. And you think that the system is doing a very good service for you. Okay. Now the second one is Amazon Echo. So I think they have this product for a while already. You can talk to the device, and the device will also try to learn what you need over time and try to guess what your potential purchase might be and do things for you, such as purchase the detergent for you, for the family, at a regular basis. So this is Amazon Echo. And the third one is Quantena. So this is a personal assistance offered by Microsoft. The idea is similar. So we tried all these services. They try to learn what you need, and they try to essentially learn your behavior pattern, and somehow they can serve you better, or even serve you before you place the order. And in that case, you think that the system or the service is good because it somehow shows some sort of smartness or intelligence. Okay. All right. So these are the sort of motivating examples, and so that's good. But then, despite all these sort of success in the industry, we somehow still have many questions for which we don't know the answers. For example, I think here we look at the two of them. The first one is, suppose I give you two systems that are claimed to be smart. How would you compare them? And for that, we need some sort of a criteria so that I can compare different systems. And the second one is, what factors actually determine the smartness or smart level of a system? So how can we sort of at least quantify the effect of the factors of a system? All right. Okay. So that's pretty much a motivation. And in this talk or in this work, essentially we want to at least attempt to answer the following questions, or take the initial step. So our goal is the following. So we hope to develop a metric for measuring system intelligence. Okay? And then we also hope to understand the roles of different information, different factors. And also we want to design algorithms such that if I'm given a system or a service, I can control it to the level where at least the users should be maximally happy. Okay. All right, so we get into the model. Now for that we need a model, and here's our model. We consider a system where it's a time-slotted system. And in this system, there is a single server, which is serving, you can think of that as serving a whole bunch of users. But in this case, we consider one single user. Okay? And the reason behind that is because most of the services nowadays target for personalized service. So we think that it makes sense to consider a single user now. And also we see that it helps to do it this way. Now for this single user, it has a set of applications. So it runs a set of applications. You can think of that as being either doing some sort of searching, or it's watching video online, or doing some other things. Okay. Now for each of the application, we assume that its demand is governed by the two-state Markov chain. Simple two-state Markov chain. It's on-off. 1 means there is a demand in that time slot, and 0 means there is 0. Okay. And the parameters are epsilon and delta. So as shown in the figure here. So this is simple. And so here's the part that we try to take the smart level into account. That is, the server at every time can decide to do two things. The first thing is, it can decide whether or not to preserve a potential demand that's going to come in the next time slot. And if it does that, and it's successful, the user is going to get a reward Rm of P. Okay? On the other hand, the server can also wait until the user places the demand and try to serve him or her in the next time slot. In that case, it's safe because I know that the demand I serve is going to be the demand. In that case, the user is going to get reward of RM of C. So here the idea is that if somehow I feel that the system knows what I want beforehand, I feel that the system is smarter. And here, so RMP is assumed to be greater than RM of C. Okay. All right, and then just to capture the randomness in the system, which might affect the service quality, we also use a system state S of T, and you can think of that as being some abstract state of the system. Essentially describes how sort of congested are the background services that might affect your service quality. Okay, and we use pi of k to denote the probability that the system state is in a particular state. And then service cost, it consists of two parts. The first part is the service cost you need to spend for pre-serving something in the next time slot, and the cost you need to spend for serving something in the current time slot. Okay. So maybe in the current time slot, the user actually placed some order, so I need to fulfill that. All right. And then we define the following metric, which we define the intelligence level of this system as the solution to this optimization problem. That is, we use I of rho to denote the intelligence, and it's defined to be the maximum. It's the maximum average reward we can achieve over all possible control policies, subject to the following constraint that the cost I spend should be no more than a parameter rho. Now, so here, as I explained, this RMP greater than RMC is to capture the fact that, well, if the system can preserve my demand, I would think that it's smarter, and I feel happier. And then this cost, we believe that it's important because a system can do some dumb things, such as I can pre-compute all possible values you might need. In that case, I waste a lot of resource, but you still get your answer fast. In this case, this should actually not be something a smart system would do. Okay, all right. So at least I hope that I explained the model clearly. So you can see that the model actually can be used to model the applications I presented at the beginning. All right. Okay, so before I get into any of the results, let me mention some of the related works that are related to controlling a system of this type or maximizing the intelligence level. So first of all, the problem largely belongs to a network control problem, where I think many of our people here at MobiHoc has done great work in this literature. But most of these works, they don't talk about proactively serving user demand and don't talk about the impact of that. And recently, there has been some work on proactively serving jobs. But mostly the prior works care about how to utilize that to reduce delay or to increase throughput. They don't talk about the impact of predictability of users, and they also don't talk about the potential benefits of learning, which we'll use in this work. Okay. All right, so this is the model and the current status. Let's look at some of the results we can get out of the model. Now, the first result, sorry for the equations, but it's actually quite easy to pass. So the first theorem says that the maximum intelligence level can be exactly characterized by the following optimization problem. It looks complicated, but in fact it's not. So let's see. Sorry, here I just want to highlight that this AM of I is the probability of getting into a 1 state in the next time slot. Okay, so if you're in 0, it equals epsilon. If you're in 1, it equals 1 minus delta. So that's just to clarify that. But if you look at this optimization problem, this part is actually the reward. It's the reward generated by your action. And this one is the cost generated by your action. Okay, so in that sense, it's sort of intuitive if you look at it. So we maximize the reward subject to cost constraint. That's nice. What's more interesting is the following. So if you look at this parameter here, you see that the AMI value, if it's larger, actually means that your objective is larger. But if you look at this two-state Markov chain, when this value is larger, essentially it means that the Markov chain is more predictable. And it's more predictable, it's more predictable the fact that it's more predictable will lead to the fact that the intelligence level is higher. So essentially it means that how smart the system is for you depends on yourself. This is something we find interesting, and maybe it's also intuitive. So for people who are more predictable, the system can guess you well so that it can serve you better. For people who usually flip a coin and do things, such as myself, there is zero hope. All right. Okay. Now, and then the second thing we can get out of this is that if I look at all these quantities together, this essentially means the long-term fraction of time that the demand is going to be in 1, roughly. If you look at that, it essentially means that if somehow the user has larger demand, then the system has more chance to impress the user. So that will also increase the perceived level of smartness. And then, of course, the third one is related to the cost. The idea is that if I can manage this part well, it's more flexible for me to preserve the user as well. But that's nice. Essentially, it means that this part, I think, is somehow or somewhat echoes the fact that bigger companies have the advantage because they're more flexible in controlling their cost. Somehow they can amortize that somewhere else. So I should go faster. All right, so this is a figure I want to show you, and I think it's pretty easy to memorize. So the idea is that we fixed a Markov chain to be a symmetric Markov chain, and we let epsilon equal to delta. In this case, the steady state distribution is the same. It's half and half. But as I vary the value of epsilon, we see that the entropy changes, and the entropy is max here when everything is half-half. And you can also see that the intelligence level is lowest here, which is sort of intuitive, like I said. Larger entropy means the system or the guy is less predictable, in which case, don't expect to get good service from the system anyway. All right, so that's the bounds and the intuition, I think. And next, we're going to design an algorithm to try to control the system well. Okay, we know the bounds, and we try to achieve that as we could. Now, there are a few challenges. First of all, we don't know the statistics. So somehow we need to learn that. And at some point, we need to learn it to an extent that it's accurate enough so that we don't make stupid decisions. And also, the Markovian dynamics is going to cause some problem. And also, there is one more thing we want to do, that is, we want to also understand the user population effect. By that, I actually mean the following. Suppose we have a large number of users which can generate equivalent samples. Now, how can we utilize that, and how would that affect the performance of our algorithm? Now, so I would design I still have. All right, so let's first define some of the metrics. So I'll go over them one by one, and hopefully we will quickly get into the algorithm. So we define the effective reward that is intuitive. So if I decide to preserve, then my effective reward will be the success rate times the preserve reward. Okay. And if I don't, I just multiply that by MC. Effective cost is similar. If I decide to preserve, then the cost I pay is the cost I pay now. If I don't preserve, the cost I pay is the demand rate times the expected cost I have to spend in next time slot. And we also define a deficit measure, which is essentially the effective cost minus rho. Remember, we want to make sure that the cost is no more than rho. Okay. So this is the deficit measure. And then we also define the following scaled dual function, which is slightly more complicated, but it's essentially just the dual function of that optimization problem I show you, the complicated one. Okay, so I will not go over all the details, but for now you just remember that it's the dual function of the optimization problem. That's it. And by scale, I mean we scale the objective with the parameter, which will determine our trade-off. All right, and then we also talk about learning. So in this algorithm, we learn the demand as follows. We specify a learning time t, and then we use this effective number of demand samples, n of t, to denote the samples we can get from the users. That is, within this t time, we get these many samples of the demand. Or you can think of that as we get these many samples from the Markov chains. And then we use a maximum likelihood estimator, or you can use some other things you prefer. But here we use this, which is simple. Essentially, I'm just counting the transition times. Okay, and then I use that as the estimates for the parameters. Now that's done, and then we have the following algorithm. I should be doing okay in time. Okay, I'll be done soon. So, and then we design the following algorithm. We call it LBISC. It's a short acronym, but I forgot what the full name is. It has two parameters, t and theta. T is the learning time we use to learn the samples. And theta is used here, which I explained. So it has three steps. The first step is to estimate the parameters, just like I mentioned. We collect the samples and we just do an MLE, and you get the estimates. And then we use a step called dual learning, which is as follows. Now I take that dual function I showed you in the previous slide. I replace all these statistics with the estimated ones. And then I solve that dual function, I get the optimum multiplier. And that's this step, gamma t star. And then I do control. Control is done as follows. I first define the cost differential. So this is the cost I need to spend. And then I do a max rate-like algorithm to choose the actions, the pre-serve actions. And here, the multiplier is plugged into the system here. And I also subtract that with theta, which is, the intuition is that I add a parameter theta. I try to estimate that exact or the target Q length the system should be operating at. By adding that the multiplier, essentially I can subtract out many of the Q lengths I need to build up. But then I also need a theta because I want to create room for the Q to fluctuate. Eventually I get good service. That's a high level idea. And here, like I said, essentially I balance cost and reward. If the reward differential is better than the cost differential, then I'll preserve. Now here, if you look at these steps, they also nicely correspond to the sort of common approach of controlling systems nowadays. The first part is about data, and the second part is about training your model, and then you do the control. Okay. And this dual learning part is also where your data meets control. So I collect the data and I crunch out some numbers I can use in my control algorithm and apply it to the system. I get good results. And this I think I can skip. I should skip. All right, so we can prove the following. If I choose a parameter is right, I think I skipped the exact numbers, but we can make sure that the deficit Q is stable. That is, we ensure that the cost will not violate the control budget rule. And then we can also show that the intelligence level you achieve can be pushed arbitrarily close to the optimum as you increase the v-value. Of course, at the cost of, so you can see that if I increase the v-value, these two terms will become smaller. But of course, your Q will also grow bigger. Okay. Now, and then the next result talks about convergence. That is, how long does it take for your algorithm to converge? Okay. Now, in this case, what we can show is that this bound is quite similar to the resource deficit bound. Essentially, it scales as follows. So if, it's like v log v squared divided by square root of n of t. Okay. Now, this is the convergence time for the learning-based algorithm. If you don't learn, it's a linear in v. Okay. Linear in v. I should also clarify that this linear in v assumes the statistics beforehand. Okay. All right, and so here I also want to comment on the results. N of t appears as a square root thing here. If you look at that, it's also sort of natural in the sense that a larger N of t will get you a better performance. That is sort of natural that if you have a large number of users who can generate a lot of samples for you in the same amount of time, then you have the advantage of learning people better, and you can get better performance. Now the convergence time, I think I can skip. So here the key factors are the three things: data, learning, and algorithm. Okay. I decided to add these comments. So if you see that some applications are not serving you well, so don't blame it too soon. Use it for a while and maybe it will serve you better later. All right, simulation results. I should be done in 2 minutes, hopefully. Um, the first one is that, so we simulated a simple case where we have 3 applications with different reward parameters. Now here it shows you that as you increase the resource, at some point the amount you can achieve will saturate and you cannot further increase it. This is sort of intuitive. So after I have enough resource, I pretty much exploited most of the predictability of users. And after that, any additional investment would not get you more out of the user. And this one shows you the algorithm performance. Well, essentially, it says that, so here, let's look at this one. This blue curve is an algorithm which does not use learning, but it assumes all the prior statistics. In that case, we see that the deficit will increase as we get a better performance in the intelligence level. But if you do learning, you can manage that deficit well. Okay. So learning actually helps. All right. So one more simulation result, and I'm pretty much done. So here I want to show you how long it takes to converge. So the blue curve is the algorithm which, as I said, it knows all the statistics, but it does not learn, so it takes this much time to converge. And the red curve is our learning algorithm. So we spend this amount of time to learn, and then we do the learning, and then we run from here. We can see that it converges faster. So learning actually helps if you use your data sort of in a proper way. And also the actual deficit would be smaller if you do learning, because you can subtract out most of the queues you need to accumulate. All right, so summarize. So we presented a framework and a normal metric for measuring how a system is smart is. Some message. The first message is that I kind of like this one. So the perceived smartness is determined by yourself. So if you're not very happy with service, well, there is a reason. And then key factors, predictability, demand, and resource management. And also we presented a learning-based intelligent control algorithm, LBISC. Essentially, it shows that you need 3 components to get good performance: data, learning, and algorithm. And also what's interesting is that the user population has a square root effect on the performance. So if you have more users, which is, you certainly get a better performance if you use it right. Okay, so that's pretty much about the talk. So I think I'll end my talk at this particular slide. Sorry for those who already see this slide. So we have a JSAC special issue coming up. You can check that on the JSAC website. And all of you are welcome to submit papers. All right, I think I'll stop here. Thank you.